Hello everyone, I am Dr. Belmont and today's video is about advanced organic chemistry and it's for my special topic courses. So let's go to our drawing app immediately. Very well, as you can see I already have something drawn, right? Because you can see the structures are a little bit big and the screen is not as big as I would like to. But I want to center our attention about the name of this compound, which is chloroquine. Right now, chloroquine, I hope I am pronouncing it correctly. Chloroquine, I think, is going to be a major subject of interest in the closest future due to the properties that this anti-malarian drug or medicine have present in the past months, right? And as you can see, we have already the structure here on the top of the screen. And let's see where we can make this connection to properly identify the symptoms that we require for the synthesis of this molecule. So first of all, what about if you disconnect this? That's pretty easy, right? And what about if now we disconnect that? Very well. So pretty simple, right? From the 3 nitrogens that this molecule has, we have disconnect 2, and we had ended up with this particular structure, right? This particular syntone. So let's go again and try to, in this small space, draw the syntone that we're gonna get. So something like this with the chlorine here and another aromatic ring here with a nitrogen. So it's a pyridine, 1, 2, 3, 4, 5, and 6. There you go. And then something like that, right? And here we would have our positive charge for the syntone. So let's count 1, 2, 3, 4, 5, 6 member rings. Perfect. Not the best and most looking, but works for our purposes, right? So we need to figure out a way in which we can synthesize this syntone. And if you go into the literature to see what we can use, right, to synthesize this syntone, we would actually have to go and look for the synthesis of quinolines, right? It's going to be spelled here, like key with you, quinolines, right? And there's a very specific route that we can use, which is the route of Gould-Jacobs synthetic route, right? And the compound that this synthesis use is right here, right? This one that you see here. And the name, I had to type it because it's a little bit long, so I think it was easier if we just typed it. It's ethyl ethoxy methoxylene malonate. And so it's basically a derivative from the malonic acid. I'm going to have to ask you to look for a synthetic method for that because probably we will discuss it later. But right now, to what we care for the most, which is the synthesis of quinolines. Very well, so let's try a new page. Excellent. And let's go and draw our syntone. So we have our syntone here. The chlorine. There you go. With the other 6 member ring. There you go. And a positive charge here. Okay. So if we perform a positive charge here, that means we need something that is going to leave. So for example, it could be a leaving group. Right now, let's go and perform a chlorine, right? So instead of having a syntone, we have actually a synthetic equivalent from the syntone. And now the question is, how are we going to be able to get this one? Well, retrosynthetically speaking, what we would have to do is to disconnect here, right, and transform what? A phenol. We already know that because with an halogenic agent, we can transform this OH into what? Into an halogen. So now we have to figure out how are we going to synthesize this quinoline. And actually, believe it or not, is more simple than you might think. And the disconnection, well, it's part of the class. We're going to have to perform a disconnection here, and we're going to have to perform a disconnection there. So let's go and open another page, take our pen, and write down what we are going to need. NH2 and Cl. So somehow we need to create a ring, right, between these lone pairs and this carbon here. So we need to figure out how to add how many members. 1, 2, 3, 4, 5, and 6. So we need to add 3 more so we can connect and have our pyridine cycle. So how do you think are we going to do that? Well, that's why we're going to use the malonate derivative to perform that reaction. So let's go again and type down this reaction. Give me a moment. So I'm going to have here my chlorine, my nitrogen, and my malonate derivative. Very well. So the structure actually is going to tell you pretty much where the nucleophilic attack is going to happen, right? If you remember your course of Organic Chemistry 2, we have a double bond here, we have a double bond there, right? And they are conjugated, so we will target for something similar to the Michael addition, meaning that these electrons are going to go push in, push back, right? And we're going to create an intermediate for the reaction. Give me a moment. There you go. And the next step of the reaction, what we're going to get is something like this. I'm going to reduce the numbers, okay? The formulas, so I have a little bit more of space. So I'm going to have my chlorine, my nitrogen, now attached to a single bond, the O-ethyl, right? A double bond, the oxygen, that is negative, another ethyl, right? And the rest of the carboxylic acid. So I have CO2, see? A little bit more of space. So I have this negative charge, right? And this nitrogen is going to be, of course, bonded still to some hydrogens. So it's going to be positive. As you can see, we have a negative charge here and a positive charge there. So the charges are balanced. So we're doing something good at least. And the obvious stage is that these electrons go back, right? Because we have a double bond that is conjugated and get more stability. So these two electrons should jump here, right? And what would happen if these ones go back? Well, we go into an equilibrium, which actually happened, but since it is not what we are looking for, the only option that we get is that the ethanolate goes and leaves like a leaving group. So let's see what we end up with. Very well. And what we will have is first our pen. There you go. And I end up with basically the same framework. Sorry, give me a moment. I'm going to erase everything. It's not working. Give me a moment. There you go. Okay. And then our amine, right, which still is attached, right, to two hydrogens. And what we get actually is something like this. So the ethanolate, right, was substituted by what? By our amine. And we still have an ethanolate, which, as we know, it's a powerful base, and there is a negative charge that is going to help us to go pick up and neutralize the charges. So what is going to happen is that these electrons are going to move towards the nitrogen again, right? So we will get basically the next structure. 1, 2, 3, 4, 5, and 6. There you go. Chlorine. Nitrogen, now only attached to one hydrogen, attached to a carbon, right? A double bond. And the rest of the malonic acid derivative. Plus HO. There you go. Excellent. So look at this. I don't know if you see what we have been able to attach, right? Because we were looking for a 6-member ring, right? We had to attach 3 more things. We already had 1, 2, and 3, right? With this nitrogen, we have to add another 3. I don't know if you can see them, but it's pretty obvious that we're going to depend into what? Into 1, 2, and 3. You see? So the other carbons that we need to follow to close the cycle are exactly these ones, right? That meaning that this is going to be also what? another leaving group, and we will have to figure out how to transform the rest of the structure, but we are already going pretty well. So how are we going to do that? It could be challenging, right? Let me erase this. There you go. I'm going to write it again. Attach to oxygen and to carbons. Sorry, no, that's horrible. Give me a moment. Oxygen and 2 carbons. There you go. So, well, we have a nitrogen, right? And we need a driving force movement of electrons that is going to help us to perform that. So remember that what we want to do is a cycle of 6, and that will get resonance. So resonance is going to be the driving force of the reaction. So these 2 electrons are going to jump into, right, the aromatic ring, and when that happens, these 2 are going to be pushed towards the carbonyl group, pushing, right, the electrons towards the oxygen, bouncing back to the carbon, and when that happens, these ones will go toward these 2 electrons, right, that create a bond, will move towards what? The oxygen. So we will have again another ethanolate as a leaving group. So let's use another clean sheet of paper, well, virtual sheet of paper, and see what we will get. So the resultant structure, for that I need my pen, is going to be this. So I will have 1, 2, 3, 4, 5, and 6, right? And Cl. 1, 2, 3, 4, 5. The nitrogen now attached. Finally, we have it attached, right? But here we have a hydrogen. These 2 remain conjugated, and we have a double bond here, right? That was were the electrons that the nitrogen used to push and perform the reaction. And here what we have, well, is the carbonyl group with a double bond here, and still here another carboxylic acid. An ester attached. No? We will transform that into carboxylic acid into a moment. But we still need to do, before that, we still need to do something with this, because nitrogen doesn't like to be positive. So it's pretty simple, right? Remember that we still have what? An ethanolate flying, right? Somewhere there, and it's a powerful base, so it's going to pick up this hydrogen, and then these electrons are going to jump, and then these electrons coming back to the nitrogen, right? And we have a very stable aromatic compound, or semi-aromatic compound. Now, you will see what I'm talking about in a second. So, let's go about and see what we would get. So it's going to be 1, 2, 3, 4, 5, and 6. Again, horrible. Give me a moment. So it's 1, 2, 3, 5, 4, 6. There you go. My chlorine, right? 3. The nitrogen, right? This attach, this attach. There you go. And the nitrogen again with the hydrogen. So what do you have here? You have here a double bond, you have here a double bond, and another double bond, and they are conjugated. But are they aromatic? No, I really don't think so. And that's a problem. That's a problem because we have a cycle of 1, 2, 3, 4, 5, and 6. So according to the Huckel rule, this has to become aromatic. And as you can see, it's going to be very simple, because again, these electrons of the nitrogen can just push in, then drove in, and these ones, right, will go there. At the end, what we will have here, it's a negative charge, right? That literally what is going to go pick up this hydrogen, and then these electrons will go back to the nitrogen. So let's go and see what we are going to get. Another page, please. There you go. And my pen. Thank you. So I have 1, 2, 3, 4, 5, and 6. And my chlorine, right? So look at this. The end-up structure is actually something very similar, right, to the synton that we were looking for. but we still need to do something about this. But that will be in the next video, because I think this has already been long enough. So we will end up here and see you in a moment. Bye.